Java organizes software through a simple hierarchy. Developers write instructions inside classes and group them into folders called packages. While perfect for a single directory, it fractures at the enterprise scale. Scaling to millions of lines creates a massive, chaotic web. Prior to Java 9, the language lacked a mechanism to truly hide public types. Any class marked as public was accessible to any other piece of code in the entire application, even if the original developers intended for that class to remain an internal tool. Without internal boundaries, developers tied new features to fragile internal components. A single change could ripple outward, making massive codebases brittle. This open access environment created a second problem for engineers: implied dependencies. An application could rely on a specific third-party package to function without any formal declaration of that reliance existing in the source code. Since code didn't declare what it needed, a missing piece wouldn't trigger warnings during development. Developers would only discover the missing dependency when the software was already running, causing the application to crash. To stop these unpredictable runtime disasters, engineers needed a higher level of architectural aggregation. They needed a way to enforce boundaries and map how different components connect. That solution arrived as the Java Platform Module System. It introduces a module, a vault that sits above the package level, grouping closely related packages together into a single protected unit. To govern this vault, developers use a centralized rule setter, module-info.java. By default, this file enforces strong encapsulation. Every internal package is locked down and hidden. To share a specific tool, they explicitly write an exports command, opening a gateway through the boundary. Without this explicit directives, the module system prevents outside code from accessing those internal packages, keeping implementation details protected. For a main application module to access those exported tools, it must take an active step. Access is never automatic. The main module must declare its need using a requires directive. This acts as a formal contract, locking in a connection between the two modules. The result is a balanced system. A module controls what it shares via exports and defines what it needs via requires. These strict declarations are mandatory because they change how errors are discovered. They shift the discovery of missing dependencies from the unpredictable runtime environment to the stable compile time phase. The compiler now validates the entire module graph, halting the build process if a requires or exports contract is broken. This verification ensures that the core dependencies defined in the module-info file are accounted for before the software ever runs, removing the primary cause of historical dependency crashes. Mapping out these explicit dependencies does more than prevent crashes. It allows the application to be reduced to its necessary components. Because every relationship in the code is perfectly charted, developers can safely strip away massive parts of the underlying Java platform that their modules don't explicitly require. This process allows massive enterprise applications to be optimized for small embedded devices or cloud environments. Java modules provide a structural contract that ensures modern code remains secure, explicit, and highly adaptable.